Here you see LTspice circuit model. Oops. And here I have a MOSFET, which is used as a model for biasing an amplifier stage. So what am I doing here is exactly this picture that we have seen before in the presentation. Here I have a current, and everything is parameterized. So even the MOSFET parameters, you see the length is L, the width is W, and the number of devices is the small m. And here you find the parameter definitions, the length and the VDS and the operating point that I want, everything. Oh, sorry. So here this device is biased, and this voltage controlled voltage source generates the voltage VGS required to generate here approximately 0. You can see that. Let's say if I do a operating point information. So I replace this AC with dot op. Okay, and I then run. Then it gives me the operating point information, and it tells me about this is the 544 microvolt. This is 544 millivolt. So this needs 554. This one is 1K, the gain. So this is quite nice biased on 0. And this voltage is just copied to a voltage source here with a voltage controlled voltage source gain unity. And this is the VGS. And now I connect here a source, a current source in parallel with the source resistance. And I want to measure the transfer from this amplifier stage from current to voltage. And you see the voltage, the load is nicely connected to ground. There's only 71 microvolt here because, well, there should be 0. There was, when it was open, there was 544 microvolt, and this resistor is 10K. So there is hardly any current flowing here, while IDS is 100 microamps. 100 microamps over 10K would be 1 volt. So it is really nicely biased. We have only 71 microvolts, so a very, very small offset. And if you want to have it smaller, you just increase the gain of this voltage of E1 voltage controlled voltage source, as long as it converges, of course. Because if you make it 10 million, maybe you create a situation that LTspice cannot calculate it anymore. And now you see it's 54 microvolt and here 7 microvolt. So you can go on and on and on and on, trying to reach 0, but then for that purpose, you would, of course, need a nuller. But now I can do an AC analysis. AC is a little bit a confusing word in simulation because it's also valid for DC, but they don't simulate DC. AC means small signal in SPICE. It takes the derivatives of all the nonlinear relations in the operating point and then calculates the transfer. So AC is because it's always used for small signal analysis, but small signal analysis would be the good word. AC is basically a confusing word, but everyone is used to it now. So that's why people are doing it. I know you are, I guess you are familiar, so we can edit the simulation command and do an AC analysis. The type of sweep, we want to have it per decade, number of points 20, the start frequency 1 kilohertz, and the stop frequency, well, let's do 10 gigahertz, 100 gigahertz, why not? We are okay, and we can place it there, sorry, and run the whole thing, and then measure the voltage at the load. And this is, let's say, it looks like, of course, the trans impedance, because we have current and the source impedance is very high. It's like 10 mega ohm. So setting a limit here, but basically if I make 10 mega ohm larger, we would get a real integrator there. And then we have, so this is basically the first pole that should be in the origin if I was driving from an ideal current source. But that is difficult in SPICE because then this current is flowing into a floating node, and that is not allowed. So anyway, you need to place a resistor there, but maybe the 1 tera ohm if you want. And here you see a second pole and a 0. And now you can't see very well maybe the dots of the phase characteristic. Can you see the dots of the phase characteristic, Chris? Is it visible?
Yes.
Okay, if you look at the dots on the phase, then here we go to 90 degrees. It was 180 degrees, of course. Here on top, you see 180 degrees. It goes to 90 degrees because it was inverting, and it drops to 90. And then it immediately goes to minus 90. And you would expect if there's a pole, it will go from 90 to 0. But it goes from 90 to minus 90 because this is a 0, but it is a 0 in the right half plane, exactly as we have seen in the analysis. So the 0 in the right half plane lets the phase characteristic go as if it was a pole. So we have in totally 270 degrees phase shift in a second order system with a 0 in the right half plane. Now you can use this kind of circuit to bias any FET at any current or voltage you want and connect loads, whatever you want. And so we can use this as a starting for example, input stage and output stage of our antenna amplifier later on.